Welcome. My name is Bob Tickleman. I'm a Microsoft technical trainer, and I'm excited to be your guide for Learning Path 4, Develop Solutions that use Azure Cosmos DB, part of the AZ-204 course. We're going to take a look at two different modules in this, and there'll be two separate recordings. This recording, the first, is going to explore what Azure Cosmos DB is. In the final recording, we're going to take a look at what you can do with Azure Cosmos DB and the ways that you can work with it. Getting into module number 1, we'll explore what Cosmos DB is. And we're going to take a look at where it fits into the data structures that you have, from lightly structured data to highly structured data, things like SQL itself. And where does it fit in amongst other solutions like Azure Tables and Redis Cache? So I'm going to do some demonstrations showing how to create the Cosmos, as well as its feature sets and why it's such a compelling reason as a technically new resource that has never really been available to you in the traditional on-premises environment. So getting into what Cosmos DB is it says it's a fully managed global service. In other recordings, you've heard me talk about regionally based services. Things like Microsoft Entra ID is a global service. It's the same service globally. Any changes you make there are globally replicated. We saw that through other recordings. We looked at things like app service plans, which were regionally based. We saw things like storage accounts that were regionally based. So Cosmos DB is a global resource that allows you to deploy a solution and then have multiple copies of this globally deployed through a single pane of glass. And we'll show you this as we get into the demonstrations. And it provides at a scale unlike any other lightly structured data that has ever existed. Things, as I said, like MongoDB and Cassandra and Gremlin. These services have been around for a long period of time on premises. And we're going to take a look at how this global service provides for both elasticity, for scale and replication, to have it replicated globally, but also dynamically scaled to meet your needs at a scale and latency that has been unprecedented in the industry. So when you take a look at some of these characteristics of what makes Cosmos DB unique, as I said, it provides a global replication model that will now automatically replicate this data, not just within the region. And the books will talk about similar to a storage account, there are multiple copies of that data within the region where you're going to create the primary instance of your Cosmos DB, but then you can replicate that information literally around the globe to almost every data center on the planet, and now have that information normalized so it's the same everywhere, so you don't have to have your European applications come back to a central location or wait for a latency of some replication to get that data over to that geographic region. So huge global replication capability at a massive scale. And it provides a variety of different consistency levels. And I'm going to do a description of what the two traditional ones are that we've had for many years, using things like SQL. In a highly structured model, we had the capability of working with master copies in different ways to have what was called strong and eventual replication. Now, as a developer, you might not worry about this too much, because at the end of the day, the strong replication gave you the most consistent data. And it just meant that from an application perspective, the current data might not be available anywhere until it's strongly replicated. By picking another replication model, it would require you as the application developer to build some code to handle that eventual replication. And that's the example I want to get into and describe to you to understand where this happens. And then we'll discuss these three new versions of consistency that Cosmos introduces and how it might fit into both the data design as well as your application design to gain access to that most relevant information. When you take a look at latency, and I'll draw some of these numbers up as I talk about the different use cases of things like Azure Tables that have things like 20,000 IOPS. You take a look at something like Redis Cache that has like upwards of 160,000 IOPS for information to that lightly structured data. Cosmos DB gets into the hundreds of thousands, even millions of transactions per second. In fact, there was a couple of years ago that Microsoft set a world record in the number of transactions with a little over 1.5 billion transactions in a single day. So massive capability with low latency And you can see the numbers there, sub 10 milliseconds to replicate that information, as I said, globally around the world in that 99th percentile. And then that elastic scale-up capability. You can start off small and start to work with it and then add regions to this to provide for this massive replication. Now, we don't get into it in this course at all, and you may want to take some of the other courses that we have that talk about data construction and the configuration of partitioning of your data. I mentioned a couple of those terms in this lesson, but we don't dive deeply into it. Just know that they are covered in other courses, but not necessarily this one. So diving a little bit deeper into these specifics, I'm going to go off to do some whiteboarding, and I'll come back and revisit a lot of these concepts because I think that they'll make more sense for you. I want to start with a general construction about your application design perspective. And you might have seen this in other recordings if you've been watching this series, but we've taken a look at the different models for developing applications. And we've talked about having a monolithic style where you would build a monolithic application that had large scale applications. And the example I've used in the past was something like Exchange with 30 gigabytes that did thousands of different features and functions. And all of those different features and functions were bottled up or packaged up in a single application. Now, at the end of the day, with Agile and microservice development, I can still have the exact same application, but instead of bundling them all together, each individual feature or function that I'm looking for that made up that total monolithic application are now built as these microservices. We talk about separating them across the 3 tiers that we take a look at in N-tier architecture planning designs of where you have some front end or system of engagement, which your users are going to interact with. You have some business tier. And then you get some back end or data tier or system of record at the back end. Now, what might have happened in the past, and we've talked about this in other recordings, you might have a www page. And on that www page, you've got thousands of images of the products, maybe some video recordings, you got how-tos, and those all would be stored in a storage account. We saw one of the benefits of this design and architecture is that you now provided for independent scaling. And in the modules we talked about, either containerization or app service plans, we didn't have to build the infrastructure in virtual machines. We now had the capability to scale out to meet the needs of the specific application. Now, as I mentioned, you might have those pictures coming from a storage account that would then have to exist on that page. And this is where we get into the different storage tiers. If you remember that recording, if you haven't, go take a look at the hot, cool, cold tiers that we talked about that were available for storage of things like blob imagery, videos, that static data. Now, what might have happened if I needed a list of products that I sold, or maybe a search capability. Now, I would hope that you wouldn't have queried in the back end maybe a SQL database or highly structured data. This is a traditional transactional relational database as your source of truth to store that information. Now, you could populate that search capability or the list of products from information from the SQL database. Probably not a good design. But now what you have happen is you've now got millions of requests, if it was written that way, now coming to your SQL database asking for that list of products that you sell. Now, it might be great that your front-end application can scale to meet that demand, but now you have to build a back-end database that's also going to provide that scaling capacity to meet the millions of users coming. It's probably not a good way to do that. And so we've got to still have SQL as a system of record. And this is where we get into a term called decoupling of applications. So I need to decouple the querying of that static information that doesn't change a whole bunch from my relational database in the back end that might come from one or more table queries that I might have to do. And so in my business tier, I'm going to have some form of lightly structured data. Now, we've got several forms, and we don't talk about them all in this development series, but if you go back to the storage module, where we talked about the different types of storage in a storage account, there was those static images of unstructured data. We also had a data type called lightly structured data, and we're going to refer to them as Azure tables and queues. So I have an Azure table that I have available. I'm not going to do it in this recording, but we also have our queues that I'll be covering in another recording, but I'm just going to put it in there as a form of lightly structured data as part of a storage account. Now, Azure tables can have a lightly structured, what's called a name value pair set of data. So I can now query my database once, get the name value pair of all the products that I needed to work with. Now, taking a look at the structure of that data, maybe I wanted lists of products by vendor. So I could now index my SQL database in various forms. By the default indexing might be based on the product number. But then I have the product, one of the values might be the vendor or the manufacturer of that product. So I could create a SQL index that would now have an index of the products by vendor. Now you're putting the burden of that on SQL. So one of the things that we can do, not only decoupling the data from the back end, we can also denormalize that data. So now instead of having a system of record with the information in the back end, you're going, yeah, I don't have to have the SQL source of truth. I could now have maybe a table that has products that are listed in alphabetic order, A to Z. I have products that are going to be listed from manufacturer, listed A to Z. Now that could be in a separate table, or it can be in a different partition in this name value paired structure we're dealing with. And you could do that in Azure Tables. Now, Azure Tables, as I mentioned before, have about 20,000 IOPS that they can perform. It's pretty good. It's inexpensive. It has light structured data. It provides the high availability and redundancy of Azure's storage accounts that are regionally based. Now you have some potential issues though, because now I need a global application. So maybe Azure Tables are not going to be the best solution. We saw that it had read-write capabilities potentially through a global replication through the storage account in a globally redundant read accessible. So you could now have an application go to its globally redundant read accessible version. All sorts of different ways to work with Azure Tables in a storage account. Now we don't cover it in this course, but we also have a feature called Redis Cache. Redis Cache has been around for a while. It's not a Microsoft product. Microsoft provides Redis capabilities that now provides higher performance capabilities than an Azure table. It's going to get you upwards of 160,000 IOPS that can now provide this in that traditional Redis cache in a name value paired table structure that you can now have that information available. Or you could use Cosmos DB. This is just one example of a choice that might be made. At the end of the day, as a developer, maybe it's not your recommendation that does this, but it's going to be interesting to be able to see which connection string you're going to use to connect to which data sources. So you might have a choice in making the decision here, or it might be made for you, and you just have to know what kind of configuration I need to connect with my application. But here's the use case of where this kind of data is going to be highly available. It's in that decoupling and denormalization where you're now not going to have a system of record. This information might exist for read optimizations or write optimizations. You might write back to a table or Redis cache to maybe have that stored in a system of record or some source of truth that you're dealing with. Now, it doesn't mean that you can't use Cosmos as the authoritative source of truth for those records. It's just now going to be globally replicated. That's going to be maybe not the full relational transactional database that you're looking for. So we're going to show you in another recording, if you needed to provide some level of transaction capabilities, we'll show you how you can use, similar to in SQL, stored procedures and some automation within Cosmos to provide some of those capabilities as opposed to having them built into the SQL model. So I don't want to get into a full data conversation, but this is hopefully from a developer's perspective, giving you some of the use case scenarios of that we're going to take a look at. Now, in the past, in addition to things like Redis Cache, there's been other name structures or light structured data that's been available. Things like Cassandra and MongoDB, Gremlin, these are all other data products. Some of them were open source, relatively easy to use that you would install on a server in your location to get that capability. Now, they were going to be restricted to the resources that were allocated to that implementation that you had. So the number of CPUs and the amount of memory, the storage that was available. And they had different data structures. So they had name value pairs that you were working with in some worked with what's called graph data, some worked with document data. So there was different data structures not part of this course, that these different products made available to take this lightly structured data and making it available for you. So there's just kind of the why and where it fits into the overall picture that we're working with. I now want to go into the actual portal and take a look at Cosmos DB itself. Now, I've already created one, so I'm actually going to go through the creation process, but it takes a little bit. So you'll be doing a lab, not in this recording. In the companion recording for this, there's a lab where you'll get to deploy this. But I want to show you a bit of the steps to create it. It's fairly simple. And I'm going to then come back into a deployed version and show you some of the characteristics. So I want to come in and create Cosmos DB. And it's going to say, what kind do you want to build? And this goes back to those different data structures. Now, you can take an existing Mongo, Cassandra, Gremlin DB, and using something like Azure Data Factory, you can migrate those data sources, and we can now store them in that native format. So Cosmos DB can have graph data. Cosmos DB can have document data. So you just have to pick the data creation type that you might want to take a look at to meet your data needs, whether it's naturally being put into these Cosmos version of Cosmos DB, or you're going to take an existing deployment and migrate that information in, but we can host it in its natural format. I like to think that it's just easy to move it over, but you might have to do some data manipulation through Data Factory, but it's that ETL process that you can migrate to Azure. So I'm just going to pick Cosmos DB, and you can see that's that NoSQL or Azure Table versions. You have the workload type that you want to deal with, so learning, or is it a test or deployment? This is going to talk about the general infrastructure. The starting point, like a template, is going to start off with a simple deployment that you could always change after the fact. As with most Azure resources, you're going to have a subscription to bill it to, a resource group that you want to put it into that you can either create, and then you have to have a Cosmos account name. Now, you'll see when we go back to the slides, there's a hierarchical structure of there's accounts, and then there's containers, and then there's partitions. There's this hierarchical structure you're dealing with. I'm going to just call this class demo. Do I want to have it availability zones? And we've talked about this in other recordings. Remember that within an Azure region, you're going to get Cosmos DB storing the data multiple times, very similar to the examples we did with storage accounts. And so you're going to have multiple copies of this, and whether they're in a single data center within the region or across potentially multiple data centers in that region is what we refer to as zone redundancy. Where do I want to deploy this version? Again, it's a global resource. I have to pick a primary region that I'm going to put it out. And then we're going to take a look at capacity. And this is going to introduce a term called an RU, or request units. This is a way for us to be able to obfuscate or hide the need to be able to do some deep research to figure out what resources do I need. If you take a look at the configuration of a traditional SQL server, we have to figure out how much compute, how many cores do I need to manage this SQL database? How much memory do I need to have for the information to be handled effectively in memory as opposed to having to make disk queries? How much disk do I need, and what's the performance that I need? All of those features, IOPS, reads, writes, all of those features you'd have to configure. And in many cases, and I've done this for a number of years, we would ask the question of customers, and they go, I don't know, just give me the most that I could possibly get or what I can fit into this budget. And we had to make best guesses to the amount of CPU and memory and disks that we would have to configure to get the best performance. Now, what RUs do is they do a great job of obfuscating or hiding the need to do that. So this would be, and for me as I hope it's an appropriate analogy for you, instead of taking your money and converting it to, say, let's say you're in Las Vegas, and instead of saying, I need so much money for food, or I need so much money to bet on blackjack, or I need so much money to bet on slot machines, you could buy, take your hard-earned money and convert them into that level of interactions that you might want to deal with. And if you over-provision for food and you end up with money at the end that you didn't need for food, but you didn't have enough to maybe to go see a play or one of the shows, you have to make some trade-offs there. So imagine if you could turn that into a currency that could be used in any of those locations, whether it's to get food or go to see a show, and it doesn't matter what you use. So it uses the RU to create the kind of resource that you need at the time it's needed. So whether it be compute or whether it be memory or whether it be IOs that you're dealing with, you can use an RU for it, and you buy a whole bunch of RUs. The more RUs that you buy, the deeper the discount that you get that you could then allocate. And if you start to run out of them, you could always provision some more. So they talk about these different options of provision throughput or serverless. This is going to be billed only for the compute units that you're going to be working with, or do I want to pre-provision some of these and work with auto scaling? This is all covered in greater detail in the books, but you can see where that option is going to come from. I then take a look at that global distribution. Where do I want to have this? Do I need geo-redundancy? Do I need multi-region rights? This is another version that is going to get into the example I'm going to draw for you in the types of, is it a primary database where there's a single source of truth to create the rights and you replicate this to all the read copies, or do I have a multi-region right that I allow, say, my European users to have a read-write capability, that they're going to be able to make what's called a multi-write capability of a database. They're going to write their values and normalize them across the European region very quickly, but I eventually need to get that in North America and maybe to my Asian regions as well. And so as I said, I've got some examples of this multi-region, multi-write capability. We've got some networking features, backup policies. We don't get a lot into this at this time. This is going to be typically done by your data scientists or your data people that are going to configure the data infrastructure you're dealing with. Okay, so that's going to build a Cosmos database. Once I've got the Cosmos database built, going to the one that I already have. Once it's initially deployed, like many of the other resources we've looked at Azure graphically, this can be done in the portal, can be done through PowerShell, CLI, it can be done through REST APIs. We've got SDKs that you're working with to be able to work with all these capabilities, but I've got an overview of the resource. I've got some learning resources. This is a great way to get in and take a look at some of the stuff that I'm going to show you about. Getting into the other features that we don't cover here, taking a look at partitioning and partition keys. There's a lot of information to actually structure the data that's going to appear into the Cosmos database itself. I want to take a look at this one because we're going to talk about this in the course. We're going to take a look at the data consistency levels. Now, by default, and I'm going to do this example in a whiteboard session in just a second, traditional relational data, that highly structured data, we've worked with what's called strong versus eventual replication. So I'm going to detail that. And what we now have, and Cosmos has brought to the table, is 3 new levels of consistency. So we want to talk about those as well. So we're going to come back. I'm going to do a whiteboarding session to talk about these 2 that also brings in this multi-write copy of a database that you can work with. So let's go off and do that now, and then we'll come back to the graphical interface. So we understand that the application where it fits overall. And if you take a look at traditional highly structured data, in this case, I'm going to use something like a traditional transactional relational database. Now I'm going to go back to an area that some of you may be familiar with. And I'm going to take a look at a term that we've used at Microsoft called domain controllers. This was, for all intents and purposes, a database that then had multiple copies that allowed for the user management and authentication of user accounts. So if you take a look at, for a period of time under the old Windows NT days, we had this structure of what the thing called a PDC, or primary domain controller, and a series of BDCs, or backup domain controllers. I had one copy, or the authoritative source of truth, that had a read and write copy of this information. Regardless of where I was as an administrator, so whether I'm sitting on my laptop in the Seattle office, I could connect to the primary domain controller and make some changes. I could be a user that's working in the Vancouver office, and I could then connect to my database, but you're going to be connecting and making changes, anything that needed to make a write to the database would have to connect to the primary domain controller to make the change so that it could then be replicated to the backup domain controllers. Now, in many cases, the change would have to be replicated to all replicated copies before any change could be seen at the backup domain controllers that you're working with. So in this case, if I had a user who called up and said, I need to change my user password, that user would then go to and maybe connect from Vancouver to connect to the Seattle domain controller, change the password to something new, change it to secret. I would have to wait for that replication to take place to a series of backup domain controllers so that they had that. So regardless of where I was logging in, it would then have that new password to be able to give to the users. And in a traditional manner, it's not always what happened here, but until that replication was confirmed across all data, the term that you might hear is normalized. Once it's normalized, that originating change at the primary domain controller wouldn't be available anywhere until it was available everywhere. So that's kind of that strong model. And from an application, it didn't really worry about it because the data had to be there or it wasn't there as it in the new state until it was everywhere. So you didn't care which one you went to because we all used the same kind of data. Now, I don't know of too many SQL servers that had a vote in this conversation, but you'll find a lot of applications were built this way using strong replication models. Well, many years go by and Microsoft comes out with a feature called Active Directory. And we moved that replication model from a strong model to a multi-master model. So every copy of the database was read-write. So you could do a read-write in all locations on any database. Now, this is a bit more than what we're talking about in Cosmos, but you remember in that configuration, we talked about Cosmos could have multiple write copies, that checkbox I showed you at the start, that I can now have a multi-write master that could now make modifying changes to that information. Now, it still needed to replicate changes to all of the other data locations in which that information might reside. Now, it has a complex method to do this. I'm not going to go through all of the hoops that talked about this. There was things called knowledge consistencies checkers, and there was the up-to-dateness sequence numbers, but there was a whole process that had to determine how to normalize that data across the entirety of the data state for all the locations in which this information might exist. So if I made an originating write someplace, so in this case, I'm going to change on the Seattle domain controller, I'm going to change that password again to secret. I would have to make some changes in my application to now be able to accommodate this potential latency. So the Bob user who might actually live in the Vancouver area, he goes to the Vancouver domain controller to get authenticated, and it's going to say, hang on for a second. I am not matching the username and password because Bob put in Bob because he went away and asked the user to, or the administrator to change his password to secret. It's not going to match. And as opposed to telling it it doesn't match, the application would have to be run to say, hey, listen, on a password attempt that doesn't match, only that one, not anything else. If a password attempt doesn't match, I want you to go someplace else to see if there's an authoritative source of a change that I'm not aware of yet. And so I'm going to say that there's a thing called a PDC emulator or a PDCE. And it is a server in this configuration that gets what's called a preferential replication of any change from any domain controller. If a password change is made on it, it will give a preferential replication to immediately replicate that information to the PDC emulator. So now Bob logging onto a Vancouver server who had his password changed in a Seattle domain controller, goes to get authenticated by his Vancouver domain controller. It says, I don't see that information, but as opposed to telling you to go away because I don't have that information, I'm going to go, and I've been told to look for this thing called the PDC emulator, and it's going to get preferential application. And if it has the new secret password, I will accept that and give it to you, and I will eventually wait for that replication to come so I don't have to do this process. So there's examples of this difference between strong versus eventual and the potential implication that it might have to your application design to be able to accommodate the type of replication that was being developed for the databases themselves. Okay, so that's going to give you some idea that you're dealing with. So let's go back to the portal and let's take a look at these different replication models that are available for us. So I'm going to switch to strong here. And you'll see that the strong consistency state, see if I can zoom in here a bit just to get it a bit more. You can see that it's been deployed in US West, and you can see all the other locations that I can now deploy this to if I wanted to. And it's going to tell me the latency time. So if I try and replicate this down to New Zealand, it'll draw a line there, and it'll tell you the latency time to get that information. Should come up with a number. I think I'm hiding it. It'll tell you how long it takes to replicate that information, usually in that sub 10 milliseconds to replicate that information. But what you're seeing on the right-hand side of the slide is that replication, strong. It must appear in the same order, the correct order, on all copies before it's made available everywhere. And so you're seeing that if I zoom in here, that I've got now a location for US West 2 that has writes. I've got US West 2 for reads. I've got this also in West Central US, and I've got it in North Central. So I've got multiple copies, and you're going to see that that information appears, that a change in one location, the originating write, appears in all locations in the right order across all copies that you're dealing with. Strong. Now, I'm going to go back to the books here in a few minutes, and we're going to talk about this, but bounded staleness now allows you to configure a relationship between an originating write and another copy, and how long can they be out of a state of normalization. So that bounded staleness. And it could be based on a time factor. So I need this copy. Maybe it's a database that has medical information, and you're a part of a medical organization that has locations, across a geographic region. So I've got a hospital, in my local city, and in one building is the emergency ward, and in another building is maybe the operating room. You get rushed into a critical emergency, they're getting a lot of data that they're collecting on you, and it's going to a database that is local in that emergency ward in that building. Well, they immediately need you into the operating room, so they're going to transfer you in a couple of minutes over to the operating room, and they need that information, so they're going to define based on a number of changes or amount of time that I want these two to be in a staleness feature before it has to be considered to be normalized across. So we can now set these values for that bounded staleness. And what you're going to see now is that I've got two copies in my US West. I got my write and my read. You can see that they're tightly coupled. They're happening almost at the same time. And you can see that in my West Central, that it has a staleness. So it's still appearing in the right order, because maybe there's another hospital that's down the street and it's a little farther away. So I don't need it immediately replicated to it. But across the city, maybe I can get that information a little bit faster versus one that is several hundred miles away. It could even be longer. So you can see that the data is still appearing in the right order. We've got a tight coupling between these two, and I come into my bottom one here. It's a little bit out of time sync from the first one, and I've got this third copy in the middle here that is, again, in the right order, but it's bounded at a different time frame from the originating rights that you're working with. So bounded staleness is a new form that was never available before. Session-based, which is the default value that you're dealing with, now creates what is called a session connection. Now, if you're familiar from an application perspective, you might have session information. So a user connects to an application, that connection creates some information, and it maybe needs other applications to also be part of this session that I'm working with. And so all the resources that are going to be used within that session need to be tied together. So, this application, if it's going to go to any one of these 3 copies, I need those 3 to be tied together in a session-based environment so that if it's made, I'm going to go back to my European versus North America here, my European users connecting to a European, I need all those ones to be session bound, because the chances of it being, having in the same session coming to 2 servers that are in Europe and 1 in North America is highly unlikely, or you could just maybe not let that happen, but it's going to be based around the session information. We get into what's called a consistent prefix, and this is going to talk about the sequence in which the changes take place. And this gets into a series of other terms about idempotency and terms. I don't want to get all tied up into it, but what it's going to show you is that each change might have a different state of staleness, but the order in which some of these changes are going to take place is consistent. And so no matter how long it takes to get there, the order of operations to the changes to the data is going to be consistent across all instances of that data. And then we move to that eventual one that you're going to now see. Eventually it's going to get everywhere, but the order of operation may be different. So you can see that the red one is the first at the right, but it might actually replicate the blue, the second note here, across to another database that's in the same, but you've got a copy locally it can work with. So you can see that there might be some differences in that eventual replication that goes back to the examples I was just talking about. Okay? Similar to other storage that we talked about, you want to take some of those general concepts that we talked about in the recording for storage accounts. We have keys that are going to be available for you. And those keys are going to be the connections to the data at rest that you're working with. We talked about having 2 keys that you could then rotate the primary key and the secondary key to gain access to the entire Cosmos DB account. This will make more sense when we go back to the learning materials to see the hierarchy structure. So I can access the storage account that has a level of consistency, and I've got some keys that can work with this. I have identities that I can work with. This is going to tie me into my identity provider. So we've now seen why we need Cosmos, where it fits into my overall process and application design, and the features it's going to bring to me, and the options that I have. Do I want to work with Redis Cache? Do I want to use something cheap and easy that might be Azure Tables? But Cosmos DB is a unique feature that we haven't had before in our design that you want to consider it in many cases. Now, some people say it's expensive, but again, it gives you features that you can't have in other solutions. That elasticity, global scale, consistency across every location you're working with, speed and performance. So you're seeing a lot of those being summarized for you here on this screen. We have the Cosmos DB account, which is that high level, and this is going to come up on the next screen that shows you this hierarchical structure. So you've got a Cosmos DB account. You've got the databases that you're working with so that you could start, if you're familiar with the term called sharding. How do I partition my data up to make it most efficient? Do I put everything, you know the rule about, 80% of your work happens with 20% of your customers. So you can have 2 different partitions that you're working with, or containers, that you now partition your data up into that says, 20% of my customers are going to be in this container. And remember that term RU, I'm going to allocate more RUs to that group of data. And this other group of users, 80% of them that I infrequently use, I'm going to allocate them some RUs, but I'm going to give them a lower number. So I can get this real cost-effective use of my RUs, giving the most resources to the most commonly used data. So there's one example. You might split your data up a different way. Maybe all your users in the current year is what you care about. So you take all your users' current year and put it into a location, allocate a bunch of RUs to that. And you need this historical record information that is infrequently looked at. Maybe you put that in other parts. So all of this data structures are starting to fall into this concept of, a Cosmos DB account, a database. You get into containers, and then you get the actual items themselves. So this is a summary of the book learning pieces that get into those concepts at detail. And so this is a graphical representation. You get into your Cosmos DB account. You can have multiple databases in that account, and very similar to a storage account, you see that name structure where they were regionally based. A storage account was a unit of replication. We see that Cosmos DB is a global resource. So a Cosmos DB account is a global deployment configuration that you can have one or more databases that share a common configuration. There are then containers within there that has things like your stored procedures. We're going to cover this in another recording. A lot of those features, the triggers, the user-defined functions, those are all covered in a separate recording. And then you get into the data structures itself that you're dealing with. So that's just talking about the hierarchy of your information. The books are catching up to the conversation that we've talked about. And so we've mentioned strong versus the eventual, the types of replication that's been around, for databases for a long period of time. It's been the standard that we've had and still is when you're dealing with things in something like SQL Server, that highly structured version. But Cosmos now provides for this new item of bounded staleness. You're looking at session and consistent prefix. And so now if you say, I've got a MongoDB that I've been maintaining on premises and it's a server that's limited, I could buy more servers and work with replication and all the challenges that brings. Or I could migrate that data and now store that data into a Cosmos DB environment. And now it provides elastic scale. I can now replicate it globally that I don't have to worry about taking that local database that I was dealing with Mongo. The other thing that is great about this, and you'll see this come up on a couple of screens, is the APIs that are used to access. So I've got an application that accesses that Mongo database in a Mongo server on a local piece. Well, I don't want to have to change the data structure to move it into something like SQL and then rewrite my application to request that using the SDK to access SQL information. This is the cool feature. I can now take that long-lived Mongo Cassandra Gremlin database, migrate the data into Cosmos, and take my applications, and it speaks the same APIs. And so all I have to now do is direct the APIs in my application without rewriting the application and point it to the Cosmos database, because it will speak not just the data structures of graph and document and name value pairs. It's going to be able to speak the API languages of your application to access those data structures you're working with. This is just catching up more with some of those definitions about the major characteristics of the 5 replication types. And you'll see that it matches very closely to what we were already talking about. Now, the slide title's a little off for me. It says, pick the right consistency levels. That's the previous slide, making sure that you got the right consistency levels here. This slide is introducing not just consistency levels, it's talking about the concepts I just mentioned, the data structures themselves. And you're seeing down that far left-hand side, and it also matches the way that when you build it in a graphical interface, do I got to work with NoSQL or Cosmos DB tables? And that's going to be very simple or similar to an Azure storage account table structure. So you can start off very simply and very inexpensively developing an application using Azure tables for the development of your application. And as you start to move that through test to quality assurance and into staging and finally production, I could use table structures for all of that and then move it over to a Cosmos DB for production scale and reliability and all the features without having to incur the cost. So great ways from a design perspective to be able to get the most effective and cost-efficient methods of ways of storing that data without having to rewrite your applications. You're then moving over into that center column. It starts to introduce those other data structures that we've talked about of graph data and document data that they have depending on the different products that they supported. And this gets into those concepts I was talking about. You could take a MongoDB that you have on an on-premises server, use a thing like Azure Data Factory to migrate that data to Cosmos, and then just redirect your application to that with very little. I don't want to say it takes no work, but there's a little bit of work that you might need to get that easily working in that transition you're dealing with. And then it talks a bit about consistency levels at the far end. So go through, plan this properly, and you'll find that Cosmos DB provides a great option for you as you start to scale your applications. This is also the book learning piece that catches up with those APIs that I talked about. So regardless of what your application was written using, connecting to those various data sources, know that Cosmos DB has the capability of speaking all of those different API languages so that it can take those existing deployments and applications that you're working with little or no efforts to be able to have them be able to point towards a Cosmos DB. Now, there's some light restrictions that are talked about, not necessarily in the course material, but if you follow the product material, it talks about, is that a wire level protocol change that you are working with? So they get into a bit more detail, but just for all intents and purposes, think of it as a lift and shift, fairly simple, that might need a bit of work to make that transition very clear. Here's the book learning piece that catches up with that concept of the RU, that request unit, or your ability to provision throughputs based around compute requirements, memory requirements, and read-write I/O requirements you're dealing with. I don't have to pre-provision. I need 24 cores assigned to the server. I need 128 gigs of RAM to manage the totality of the application. That might be what you need if it's 100% busy 100% of the time. And what happens if you under-provision something? It's going to make everything suffer. So I don't have to work with that level of detail to understand. I just take RUs, buy RUs in volume, and the more you buy, the cheaper they get. And then depending on how you've partitioned your data, you allocate RUs potentially to specific containers, because that's where most of the work's going to get without having to over-provision or under-provision those resources specifically. And so we saw there is the different methods to allocate those RUs, whether it's provision throughput, whether you're working with serverless or auto-scaling capabilities to take those RUs and deploy them. So that's an introduction to the concept of what Cosmos provides for us at a global scale, this new way to store lightly structured data at a scale and performance level that has never existed before. So taking a look at the knowledge check questions, let's go through these. So what consistency levels offer the greatest throughput? I want to pause the recording for a second and check that. Now, I didn't mention this in the recording piece. We talked about how they performed and what they did, but the greatest throughput was going to be the eventual, because it only gets you what you need when you need it. So it just eventually gets it everywhere. But from a throughput perspective, that's what they're looking for if you read the documentation that goes along with that. So question number 2, what are request units or RUs in Azure Cosmos DB? Go ahead and pause the recording. So RUs represent the normalization or the standardization of all the various cost types that you might have in the form of storing, retrieving, performing compute, memory storage for quick retrieval, all of those values of the resource management that is going to be used to use, manipulate, and store your information. RUs are going to provide that for you at a consistent level across all of their potential uses within Cosmos DB. So that brings us to a close of module number 1, where we introduced what Cosmos DB is. As a form of lightly structured data, it provides a Cosmos DB account, which is a global account that you now could deploy this to all of the regions that support Cosmos DB, and then manage that at a hierarchical structure. You then can have below that, you can have the databases you're working with. Within the databases, you get your containers, and you'll hear the terms called partitions you're dealing with, and the data sharding that you might have to do from the splitting up of the data structures, creating partition keys. Not really talked about in this course. As I said, there's other courses that get into that level that now allow for your organization to take this myriad of different data sources that might have been accumulated over the years of application development of, I needed a Gremlin database, or I needed a Cassandra database for the different data structures for that kind of data that you looked for. We now have a single pane of glass, a single tool that does all of that for you, providing global scale throughput values that were never achieved before in the on-premises deployments you're dealing with. So now that you look at this, look at it as an implementation, as maybe the production level, or at some point in time, the most efficient level in your application design. Whether it's the source of truth storage records that you're dealing with, or maybe it's that intermediary decoupling to provide for optimized read and write performance capabilities you're dealing with. So you can have this massive read capability, a massive write capability, and then eventually write that information back to a database where it is going to be the authoritative source of records. But in the meantime, you've got the capacity and speed of Cosmos to make sure your application performs well. So lots of different design patterns. Figure out how it works with your application development, and we'll hopefully see the benefit of using Cosmos in your application design. Thanks for joining me in this recording. I look forward to seeing you in a future recording.